we're Team Kool Keg. I'm Mitch, and I'm the subsystem for the microcontroller.
Hi, I'm Cole. I'm working on the sensors.
Hi, my name is Jared. I'm doing the power subsystem.
My name is Dylan. I'm doing the software.
I will now be going over the system requirements. Number 1, the system shall contain food safe material. Number 2, the system shall dispense beverages. Number 3, the system shall track the history of beverage dispensing. Number 4, the system shall allow users to customize dispensing volume. Number 5, the system shall monitor the temperature of the storage container. Number 6, the system shall include a display for user interfacing. Number 7, the system shall display the current volume of the storage container. Number 8, the system shall display the dispensing volume. Number 9, the system shall include a mobile app for system monitoring. Number 10, the system shall incorporate cloud storage for keg-related data. Number 11, the system shall notify the user when the stock is low. Number 12, the system shall notify the user if the beverage is too warm. Number 13, the system shall be powered with standard US wall outlet. And number 14, the system shall be adaptable for different container sizes. It's time for the demos.
For our microcontroller subsystem, there will be two things that won't be shown. One of them is the scale, as we are not ready to fully integrate that yet, and also the EEPROM, as that has not been shipped yet.
Alright, so here we're going to demonstrate our solenoid dispensing. On the left side, we have our button with our debouncing circuit, and it's going over to our microcontroller through GPIO, which will then drive a control unit for the solenoid, which will open it. And here's an example of it working. Press the button, here open. Right now we have it set to open for 4 seconds. It closes, and then you're dispensed. All right, so here we got our test setup for the IR sensor and display. We got a tube filled with some cold tap water. On the left, we got our non-contact IR sensor. It goes to the MCU through I2C, and then it communicates to the display through I2C to update the temperature reading. There's also spaces for volume and the set dispense volume, but for the sake of the demo, we haven't implemented those yet. All right, to show the ambient temperature is reading about 73 degrees. Now we put it up to the cold water. You can see as it updates the temperature, it goes down. And the tap water is about 69 degrees, so this is a pretty accurate reading with regards to the temperature. And that's basically how it works. All right, so finally we're going to demonstrate the flow meter, measuring beverage coming out of it. We've got our Hall effect flow sensor and a bottle of water. We're going to pour the water into the Hall effect flow sensor, which will spin the metal paddles and cause induction, which then sends pulses to the MCU. And we use those pulses to count the flow and determine how much beverage is flown out. All right, so let's see it in action. And there you have it.
Hello, this is Jared with the power supply subsystem. The first thing we're going to test is our linear regulator right here without the buck regulator. First thing we're going to do is plug it in. Power is going to go through our power converter and out through our linear regulator. As you can see through the oscilloscope here, we are getting the correct output voltage for both our power converter and the linear regulator, and our voltage ripple is below 1%.
This is a screen capture under the previous test conditions. It is clear from this picture that the linear regulator in yellow has stayed within 4.5 and 5.5 volts and is a less than 1% ripple. It is also clear that the power converter in green has output 12 volts and has a less than 1% voltage tolerance.
Alright, now we're going to use this buck boost converter we found in the shop to simulate the load placed upon the system by what would be our buck regulator. So we're going to turn on the electronic load here. We are having it draw out 1.5 amps, and as you can see in the oscilloscope, Our linear regulator in yellow is still outputting the correct voltage and has acceptable noise, and our power supply is still outputting the correct voltage, and its peak-to-peak ripple voltage is still within tolerance.
This is a screen capture under the previous test conditions. It is clear from this picture that the linear regulator in yellow has stayed within 4.5 and 5.5 volts and has a less than 1% ripple. It is also clear that the power converter in green has output 12 volts and has a less than 1% voltage tolerance. Talking about the buck converter that was not demoed, this is a simulation ran on the schematic for the buck regulator in Webbench. We see that the input voltage was 12 volts, the output current is 1.5 amps, and the output voltage is around 3.345 volts. We can also see from the metrics of the simulation that the average input current is expected to be less than 0.5 amps, the ripple voltage around 10 millivolts, and that the buck regulator is expected to consume a modest 5 watts. These metrics meet our specifications that the buck regulator will stay within 3 and 3.6 volts and have a less than 1% ripple.
Alright, so this is our first attempt at integration. Firstly, we have the solenoid valve, which is hooked up directly to the power converter. We also have our flow meter, temperature sensor, and LCD display hooked up directly to the linear regulator. We also still have our representative load applied to our test buck boost converter. So now, before we open the solenoid valve, you can see that everything still meets specifications. And when we open up our solenoid, just like so, everything still works out as intended.
So as you can see, I have a DynamoDB table set up here. The table is called Kegs. And if we actually go into that table, we can kind of see what's already in there. So right now I have 3 items in the table separated with an individual ID. So each of these entries represents an individual keg with some data tied to it. Now to access this table, we actually have a Lambda function set up. And this Lambda function essentially connects the table to an API gateway, which allows our mobile app to pull from the cloud. Alright, so over here in the programming environment, you can see that I have an emulator running that is showing the current state of our mobile app. So as seen on that DynamoDB table, we only have 3 entries. So let's go ahead and generate a new entry just to show that this is working. Alright, so to generate a new entry, we're actually going to use a little Python script here that I wrote. In practice, this will be coming from the microcontroller, but since the hardware is not yet interfaced with the software, we're just going to generate some random JSON here. If we just run this little Python script here, we should be able to get a out.txt file. So let's do that. So as you can see, this output file here contains some random JSON code. This JSON includes a element with a tag of keg ID being 1 by default, but we already have an entry with a keg ID of 1, so let's generate it with a new entry. So we should have one with a keg ID of 4 now. Yep, so you can see it's a little different and we have a keg ID of 4 here. So let's go ahead and copy that, and we're going to move that over to DynamoDB now. Alright, so we're back over here in the DynamoDB database with our kegs table. And as you can see, we already have 3 entries, so we're going to just go ahead and create a new one with that random JSON we generated. Now this data wouldn't actually be random, it would be coming from the microcontroller, but again, that hasn't been interfaced, so we're just going to go ahead and do this manually here. That would normally use a new Lambda function, which again has not been written. So if we just look at the most recent entry here, we have a temperature of 49 and a volume of 248. So when we switch back over to the app here, we expect to see a new keg object here with an ID of 4, since its keg ID is 4, and then the temperature and volume should match that. So let's go ahead and restart, and then we'll hot reload the screen. And as you can see, we have that keg ID being 4, the temperature is 49, and the volume is 248. So this shows that the mobile app is working with the cloud database, and all we have to do now is make it a little prettier and then interface more with the microcontroller. As we wrap up this video, we'd like to thank you for watching and taking the time to learn about our project. We look forward to interfacing more of our subsystems in the future and completing our final design by the end of the semester.